Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, Some Basic Concepts of Chemistry. Today we will begin with lecture 12 from the course, but make sure you have watched the previous ones before viewing this one. In this lecture, we will start with a new topic called as the equivalent concept. In the last lecture, we had discussed about the concentration terms which we use in solutions. And with that, basically whatever topics were discussed in chapter 1 of the NCERT book, we have finished that. And the lecture we are going to start today, the equivalent concept. This is given in the chapter called as redox reactions in the NCERT book, but I am doing this along with the chapter 1 just because this is a concept which is going to be helpful to you to do the stoichiometric calculations. It is much simpler to do the calculations with the equivalent concept than with the mole concept. So that is why a part of this topic we will be doing here, and then we will be revising this topic and finishing it in the course called as redox reactions. So now in stoichiometric calculations, when we use the mole concept, what is the most important thing that we have to do? Well, that is the balancing of the equation. And if you remember, while doing the calculations using the mole concept, the first thing I always told you while solving the numericals was that the first step is balance the equations. Unless you do that, all your calculations are going to go wrong. Now, the beauty of this equivalent concept is that the balancing of equations is not required. Yes, you do not have to balance the equations. You are going to do the calculations without doing that. So isn't that interesting? So let us learn what is this concept. First of all, the word equivalent. What does this mean? Well, equi means equal and valent is referring to valency. What we will do is we will put 1 in between the equal and valency, and now this concept is basically meaning equal to 1 valency. So what do I mean by that? Let us learn the concept, that is equivalent concept. So we have an example as an acid-base neutralization reaction where H2SO4 is reacting with NaOH to form Na2SO4 plus water. Right? Is the reaction balanced? No, it is not. Right? But now, what is the basic underlying reaction for this acid-base neutralization reaction? The acid gives H ions, the base gives OH ions. Right? And the H ions, they react with the OH ions to form what? Water. Now, if you see the reaction H ions plus OH ions forming water, is this reaction balanced? Yes, it is. So now we can apply the mole concept through this reaction. We will have 1 mole of H ions reacting with 1 mole of OH ions, forming 1 mole of water. I hope this is fine with you. Now we can also say that 1 mole of positive charge, 1 mole of positive charge, because H ion has 1 positive charge on it. So 1 mole of positive charge is reacting with 1 mole of negative charge, that is on the OH, right? So here this is also fine. And now the charge is equivalent to the valency also, because H has +1 valency and OH has -1 valency. So we can interchange the words charge and valency. So from here, what do we infer? We can infer that one valency or charge of acid is being neutralized by one valency or charge of base. And if you take any reaction of an acid and base, this is what is going to happen. If you take H2SO4 and instead of that you use HCl, so HCl plus NaOH is also going to give H ions and then again OH ions and reacting to form water. You change the acid, you change the base, the underlying reaction remaining the same. One valency or charge of acid is going to be neutralized by one valency or charge of base. So now, who is supplying this 1 mole or 1 valency or charge of acid? It is the mass of the acid. So mass of the acid, which gives 1 mole H plus ions, this reacts with the mass of base, which gives 1 mole of OH ions. So I hope this is clear to you till what we have studied. So now we can say that the mass of the acid, which gives 1 mole H ions, is going to neutralize mass of the base, which gives 1 mole of OH ions. Now this mass of acid, which gives 1 mole H ions, this is called as the equivalent weight of the acid. And the mass of base, which gives 1 mole of OH ions, is called as the equivalent weight of the base. And this you can also call as 1 equivalent of acid and 1 equivalent of base, right? So if we now apply this to our H2SO4 and NaOH neutralization reaction, we get that 98 grams of H2SO4 gives 2 moles of H ions. Why 2 moles? This is the molecular mass, and from this we are getting 2 H ions. So 98 grams of H2SO4 gives 2 moles of H ions or 2 moles of positive charge. But what do we need? We need mass of the acid, which will give us 1 mole of H ions. So 1 mole of H ions or 1 mole of positive charge would be given by 98 divided by 2 grams of H2SO4, and this would be the equivalent weight of H2SO4. So the equivalent weight of H2SO4 is 49 grams. Now for NaOH. So 40 grams of NaOH, the molecular mass, this gives how many OH ions? 1 mole or 1 mole of negative charge. Hence 1 mole of OH ions is given by 40 gram of NaOH, and hence the equivalent weight of NaOH is 40 grams. So this implies that 1 equivalent of the acid neutralizes 1 equivalent of the base, right? So 1 mole of H ions, this is what? 1 equivalent of H2SO4, and 40 grams of NaOH is 1 equivalent of NaOH, and they both are reacting and neutralizing each other. So I hope this is clear to you all. So now let us see how we apply this to a question. The numerical says how much H2SO4 is required to neutralize 240 grams of NaOH. Using the mole concept, what do? We react the reaction H2SO4 plus 2 NaOH forming Na2SO4 plus water, balanced. Right, it is balanced. So now 98 grams or 1 mole of H2SO4 reacts with 2 moles of NaOH or 80 grams of NaOH. So if 80 grams of NaOH combined with 98 grams of H2SO4, the 240 grams of NaOH, this is going to combine with how much H2SO4? This is going to be 294 grams, right? Now, if on the same question we apply the equivalent concept, then what do we get? First of all, we do not have to balance the reaction. Then we say that 1 equivalent of the acid is going to neutralize 1 equivalent of the base. And one equivalent of H2SO4 is equal to 49 grams, and one equivalent of NaOH is 40 grams. This we have already calculated, so I hope this is clear to you. So now 40 grams combine with 49 grams, so 120 grams of NaOH will combine with how much H2SO4? This is going to come up to again 294 grams. So here your answer is the same as you got with the mole concept, but this requires less calculations. You would be able to appreciate this in some more difficult problems also. And the most important thing is that you did not balance the equation. And now if you've not balanced the equation, then even if you do not know what is the product being formed, then it hardly matters to us. Or if we know what is the product being formed, but then also we do not have to balance the equations, which is a tedious job sometimes. So this concept becomes quite helpful to solve the stoichiometric coefficients. So the advantages of the equivalent concept are that the reactions need not be balanced and we do not need to know the complete chemical reaction. Now, to make the equivalent calculations easy, we need to know one term which is called as the valency factor. We denote it by the symbol Z. In many books, it is written as N. So it is called as Z factor or N factor. It hardly makes a difference what you are denoting it with. The basic concept is going to remain the same. So what is valency factor? It is the number of H ions supplied by one molecule or one mole of an acid, or the number of OH ions supplied by one molecule or one mole of a base. Right? So like we did for H2SO4, how many H ions are supplied by H2SO4? 2 H ions. So the Z factor for H2SO4 would be 2, and NaOH supplies one molecule of OH ions, so the Z factor would be 1. So we can say that Z is equal to the number of ionizable H ions given by an acid or number of ionizable OH ions given by a base. And the equivalent weight is going to be molecular mass divided by the valency factor. So this in the symbol form we can write as equivalent weight EW is equal to MW, the molecular weight, divided by Z, the Z factor. And the units of equivalent weight are grams per equivalent. And now what are equivalents or the number of equivalents? We can draw a similarity to the number of moles. Number of moles is what? This is mass of the sample divided by molecular mass, which in short you are writing as small w divided by the capital M or MW, denoting the molecular mass. And similarly, number of equivalents would be mass of the sample divided by equivalent mass, small w divided by the EW. And as EW, the equivalent mass, is equal to molecular mass divided by the Z factor, we get the number of equivalents denoted by EQ as W, the mass of the sample, divided by the molecular mass into the Z factor. And what is mass divided by molecular mass? This is nothing but the number of moles. So we get number of equivalents equal to number of moles multiplied by the Z factor. And now a question for you. Find the equivalent mass of the following acids and bases. So how do you do that? H2SO4, the molar mass is 98. The Z factor is 2 because it supplies 2 H ions. So we get the equivalent mass to be 98 divided by 2, 49. Then we have carbonic acid H2CO3, again 2 H ions, so the Z factor is 2. So 62 divided by 2 we get as 31. HNO3, the Z factor is going to be 1. So 63 divided by 1, we get the equivalent mass as 63. Similarly, you can do this for the bases also. NaOH, the Z factor is 1. Calcium hydroxide, the Z factor is 2. And KOH, the Z factor is again 1. And now we have an exception to this Z factor calculation. We have the oxyacids of phosphorus. Oxyacids consist of oxygen in the formula of the acid. So we have oxyacids of phosphorus as H3PO4, H3PO3 and H3PO2. And if you see the formulas, you will see and you will say that the Z factor for all of them is going to be 3 because they contain 3 H ions, right? But that is not the case. The number of ionizable H ions is different as seen in the formula. Why? Because the ionizable H ions in oxyacids is that hydrogen which is attached to the oxygen. And now if you see the structure of H3PO3, you have 3 hydrogens attached to oxygen. So the number of ionizable H ions is 3. In H3PO3, we have 2 H ions which are attached to oxygen and 1 which is not. So we have 2 ionizable H ions and the Z factor therefore is going to be 2. And in H3PO2, we have only 1 H ion attached to oxygen. So here the ionizable H is only 1 and the Z factor would be 1. So H3PO4, 3 ionizable H ions, so the equivalent weight is 98 divided by 3 and this comes up to 32.67. For H3PO3, we have 2 ionizable H ions, so the equivalent weight 82 divided by 2 is 41. And for H3PO2, it has 1 ionizable H ion, so the equivalent weight would be 66 divided by 1 and the answer being 66. So I hope it is clear to you the exception as well as the general rule for finding the Z factor for the acids and bases. There is one more exception you can see. This is case of the organic acids. So in organic acids also you will see that the ionizable H ion is going to be the one which is attached to oxygen. Otherwise in the formula there are total 4 H ions, but the ionizable one is only that which is attached to the oxygen. So the Z factor for acetic acid is also going to be 1. And in the second question we have CH2COH, CH2COH, right? So here also we have 2 ionizable H ions which are attached to the oxygen. These 2 plus 2, 4, these are not ionizable. The Z factor here again would be 2. Now if a reaction is given, then the Z factor is calculated by the number of moles of H ions or OH ions replaced per mole of the acid or base respectively. So what do I mean by that? If you see H3PO4 plus NaOH, okay, so what would you say the Z factor for H3PO4 is? You've just now learned that it is 3. But now when you see the reaction, what is happening here is that we have replaced in the reaction one of the H ions of H3PO4 by sodium, right? This is NaH2PO4. It is not forming Na3PO4. So here we have replaced only one H ion with the sodium. So the Z factor for H3PO4 would be 1 and not 3, as only 1 mole of the H ion is replaced per mole of the acid. Similarly, calcium hydroxide, the Z factor, if you see the formula only, then it is going to be 2. And you will be using that too if the reaction as a whole is not given to you. So if it is given and you are seeing that in the product formed only one OH is being replaced by the chloride, the other is still in the compound, then you have to see and calculate the Z factor according to the reaction. So here the Z factor for calcium hydroxide would also be 1 and not 2. So I hope this is clear and a very important fact that you should remember. So Z factor of an acid is called as its basicity and Z factor of a base is called as its acidity. Now let us do a few numericals based on the equivalent concept. This will help you strengthen your concept which we have just now learnt. So the first numerical says, what mass of acid is required to react with 370 grams of calcium hydroxide? Now, the first acid is H2SO4, the second is HCl, and the third is H2CO3. So, the equivalent weight of calcium hydroxide is 74 divided by 237 grams per equivalent. And you know that one equivalent of calcium hydroxide would react with one equivalent of H2SO4, or similarly, for all the acid-base reactions, one equivalent of the base is going to react with one equivalent of the acid. So what we will do here is, we will find the number of equivalents of calcium hydroxide in this 370 grams first. So number of equivalents of calcium hydroxide is 370 divided by 37, 10 equivalents. And now as one equivalent of the acid is going to neutralize one equivalent of the base, so 10 equivalents of the acid would neutralize 10 equivalents of the base. And the number of equivalents is equal to mass over equivalent weight. Hence, the mass is going to be what? Number of equivalents multiplied by the equivalent mass. So now simply for H2SO4, HCl and H2CO3, write down the equivalent weights. H2SO4 98 divided by the Z factor 2, HCl 36.5 the molecular mass divided by the Z factor 1, and carbonic acid again the molecular mass 62 divided by the Z factor 2. So you get the equivalents weights to be 49, 36.5 and 31 gram per equivalent. And now to calculate the weight of each acid required to neutralize this 370 grams of calcium hydroxide, you will simply multiply the equivalent mass with the number of equivalents. So H2SO4 49 into 10, 490 grams required, HCl 36.5 into 10, 365 grams, and H2CO3 31 into 10, 310 grams. Otherwise, if we would have used the mole concept, we would have written the reactions first, balanced the reactions, and then solved by the mole concept. The next question says, calculate the equivalent weight of phosphorus acid H3PO3 in the following equation. So now the equation is given to you. So you can see the number of hydrogen ions which have been replaced in H3PO3. It is 2. So the Z factor is going to be 2. Fine. So this is why the equation seen is very important. So the number of H ions replaced is 2, the Z factor is 2. Now the rest thing is simple. The equivalent weight of H3PO3 is going to be the molecular weight divided by the Z factor, which is going to be 82 divided by 2, so 41. And now, if you are given a mixture of acids and bases, so whenever we are given a mixture of multiple acids and bases and we want to find whether the resulting solution would be acidic or basic or neutral, you will simply do what? You will find out the number of equivalents of the acids, the number of equivalents of the bases, and see which one of them is in excess. The one is in excess that is going to give the acidity or the basicity of the total solution. And in case there is complete neutralization, then the sum of all the equivalents of the acids and the sum of all the equivalents of the bases, they are going to be same. Or you can find the number of equivalents by the weight of the acid divided by the equivalent mass of the acid, sum total all the acids, and this would be equal to the weight of the one acid divided by the equivalent mass of the base, and then sum total all the bases. So this is going to come to the same value. On this we have a question. A mixture of three acids, 3.65 gram of HCl, 4.9 gram of H2SO4, 9 gram of H2C2O4, this is oxalic acid. This is made to react with a mixture of two bases, X grams of NaOH and 7.4 grams of calcium hydroxide. You have to calculate the weight of NaOH required for complete neutralization. Fine. So we now know that for complete neutralization, the number of equivalents of the acids is going to be equal to the number of equivalents of the bases. So how do we do that? It is going to be 3.65 divided by 36.5 for HCl, then 4.9 grams of H2SO4 divided by the equivalent mass 49 for H2SO4, 9 grams of oxalic acid divided by the equivalent mass of oxalic acid, which is 45. This is going to be equal to X by 40 for NaOH and 7.4 divided by 37 for calcium hydroxide. And on solving, you are going to get the mass of NaOH required for complete neutralization to be 8 grams. Next we have is a law of chemical equivalence. So we have studied so many laws, the laws of chemical combination. We have one more interesting law, that is the law of chemical equivalence. So this states that whenever two substances react, any two substances, basically till now we have been focusing on acids and bases. This concept can be applied to any two substances. So whenever two substances they react, the equivalence of one will be equal to the equivalence of the other, and this would be also equal to the equivalence of any product formed. So what do I mean by this is that if we have a general reaction, A moles of A reacting with B moles of B forming C moles of C and D moles of D. So according to the mole concept, A moles of the A, they react with B moles of the B and C moles of C and D moles of D. Right? This is how we have been doing the mole concept. But in the equivalent concept, this is very simple. One equivalent of A is going to react with one equivalent of B, forming one equivalent of C and one equivalent of D. So this is what the equivalent concept says. This is what the law of chemical equivalence says. And let us see how we apply this. So we have an example, 4A plus 5B forming 3C plus 2D. And the initial concentration that is given to us is 7 equivalents of A and 10 equivalents of B. Now you do not have to do lengthy calculations to find which is the limiting reagent and the excess reagent. You simply can see that 7 is less than 10. So the number of equivalents of A is less than the number of equivalents of B. So the limiting reactant is what? This is A. And when we are going to react A and B, the 7 equivalents of A are going to react with 7 equivalents of B. Right? So 7 equivalents of A consumed, 7 equivalents of B consumed, 7 equivalents of C formed and 7 equivalents of D formed. And as a total, what is going to be left behind? A is going to be completely consumed up in the reaction. 3 moles of B are going to be left behind, 7 moles of C and 7 equivalents of D. This is what is going to be formed as the products. So this is very simple to apply. And now an extension of the equivalent concept to salts, ions, oxidizing and reducing agents. So basically, we will be focusing our attention to only salts and ions in this course. The oxidizing and the reducing agents is what we will discuss when we do the course on the redox reactions. This I am not going to touch in this course. I am doing the salt and ion part because this is similar to the mole concept, and this is going to really be helpful to solve your stoichiometric questions. So first of all, the equivalent weight of ions. So the equivalent weight of the ions is going to depend upon the magnitude of charge on the ions. For the cations, the equivalent weight is going to be mass of the cation divided by the Z factor, where the Z factor is charge on the cation. Right, and for the anions it is going to be mass of the anion divided by the Z factor, where Z is charge on the anion. So examples, we have equivalent weight of magnesium plus 2. So this is going to be molecular mass 24 of magnesium divided by the Z factor, which is the charge on magnesium, which is 2. So 24 divided by 2, we get 12 grams per equivalent. Calcium is 40 divided by 2, the charge on calcium, so 20 grams per equivalent. Potassium 39 by 1, aluminium 27 divided by 3, and silicon 28 divided by 4. Similarly, for the anions also we are going to follow the same thing. For oxygen 2 minus, so 16 divided by 2. Fluorine F minus 1 charge, so 19 divided by 1. OH minus 17 divided by 1. Phosphate, the mass is 95, so 95 divided by the charge 3. So 95 by 3 is 31.67, and then we have chloride ion 35.5 divided by 1. So this is how simple it is to calculate the equivalent weight of the ions. And the next we have the equivalent weights of the salts. First we have the normal salts. So the equivalent weight of the salt is simply the molar mass of the salt divided again by the Z factor, where now the Z factor is total charge furnished by the salt. What do I mean by this? Let us see this with an example of Na2SO4. The charge on one sodium atom is 1 plus 1, right? But in the formula of the compound, we have 2 sodium ions. So the Z factor is going to be the total charge furnished by both the sodium ions. So this is going to be Na plus multiplied by the 2 plus 2 charge. And for sulfate, the total charge on this sulfate ion is minus 2. So the charge is minus 2. And now for the Z factor, therefore it is going to be, for sodium sulfate, the Z factor is going to be 2. So the molar mass of Na2SO4 is 142. The equivalent mass would be 142 divided by 2, which is 71 grams per equivalent. For NaCl, the charge is plus 1 and minus 1, so 58.5 divided by 1. Calcium sulfate, calcium plus 2, sulfate minus 2, so the charge is 2. So 136 divided by 2 is 68 grams per equivalent. Or another way to find the equivalent weight of the salt is the sum of the equivalent weight of the cation and sum of the anion. For example, for Na2SO4, equivalent of weight of Na plus is 23, and for sulfate it is 48. So this is also going to come up to 71 grams per equivalent. So I hope this is easy. It is very easy to calculate the equivalent mass if you know the Z factor, and the Z factor you can find out so easily. Finally, we have the equivalent weight of the hydrated salts. So what are hydrated salts? Which have water of crystallization attached to the molecule of the salt during the crystallization process. So examples being copper sulfate 5 water, magnesium sulfate 7 water, which is called as Epsom salt. Then we have sodium sulfate 10 water, Glauber salt, sodium carbonate 10 water, washing soda. So in all of these, the solvent water, this does not ionize. Only the salt is going to contribute to the charge. That is what you have to remember. So for sodium sulfate 10 water also, the charge is going to be contributed only by the Na2SO4, for which you now know that the Z factor is what? Yes, it is 2. So the molar mass of the salt, which is going to include the mass of this 10 molecules of water also. So molar mass becomes 322 divided by the Z factor 2, we get the equivalent weight as 161. So I hope this is clear to you. We would be elaborating more on the equivalent concept in the next lecture also. For this lecture, that would be all. In case you have any doubts, you want to give any suggestions, please mail to us at h2ochemistry@gmail.com. We will meet again for lecture 13 on the topic equivalent concept, lecture 2, from the course Some Basic Concepts of Chemistry from the channel H2O. So if you're liking, please do click on the like link, and also do subscribe to our courses and click on the bell icon to get a notification as and when we put up a new lecture for you. Bye for now. Have a nice day. Enjoy yourself. Thank you.